Right, so we need to define the complex conjugate. So if I have a plus bi, the conjugate is a minus bi, so only the sign for the imaginary part changes. A stays the same, the real component stays the same. And the reason we want a conjugate is because it allows us to realize the denominator if I'm taking two complex numbers and dividing them. And this is similar to rationalizing the denominator. When I have an irrational in the bottom, I also multiply by the conjugate. So in this case, I would multiply by c minus di over c minus di. So up top, I would just have whatever that product is, and it would still be a complex number. But notice in the bottom, this is a factored difference of squares, so this becomes c squared minus d squared I squared, but of course I squared is just -1. So up top I'll have whatever my product is, and then in the bottom I'm going to have real number c squared plus d squared. So that's why I call this realizing the denominator. You'll still see it written as rationalizing the denominator as well. Those things would mean the same. So let's see how we would do that here. So here, all I need to multiply top bottom by is the I. And that's because up top I'd get 4i, in the denominator I get 5i squared, which then becomes -5. That negative could go anywhere though, 4i over 5. So this fraction is equivalent to this fraction. This side I'm going to multiply by 1 minus 4i. So up top, I'm going to get for my real part 2, and then plus 12i squared. So that's going to be, I'll just write it down, plus 12i squared. That of course is going to be -12. Now my imaginary part, I'm going to have minus 8i minus 3i, so minus 11i, over 1 minus 16i squared. Simplifying, 2 minus 12, that's -10 minus 11i over 17. So this is what it looks like when I divide complex numbers. Really, I'm not so much dividing here as I am simplifying.